Question 1. What is a bitmap? Which statement best describes a bitmap image? The correct answer is B. An image represented using a grid of pixels. A bitmap, also known as a raster image, is made from many small squares called pixels. Each pixel represents one tiny part of the image and has its own color value. When all of these pixels are arranged together in a grid, they create the complete image that we see. So remember, a bitmap image is represented using a grid of individual pixels.
Question 2. What is a pixel? The correct answer is C. A single picture element in a bitmap image. The word pixel comes from the words picture element. A bitmap image is made from many tiny pixels arranged together in a grid. If we zoom into the image, we can see these individual square pixels. Each pixel represents one small part of the image and can store information about its color. So remember, a pixel is a single picture element, and pixels are the basic building blocks of a bitmap image. Question 3. Image dimensions. A bitmap image has dimensions of 800 by 600 pixels. What does this mean? The correct answer is B. 800 pixels wide and 600 pixels high. Bitmap dimensions are normally written as width times height. So the first number tells us the width of the image, and the second number tells us the height. In this example, 800 is the width and 600 is the height. So, remember, image dimensions are written as width by height, measured in pixels. Question 4. Calculating total pixels. How many pixels are contained in an image with dimensions 800 by 600? The correct answer is C. 480,000 pixels. To calculate the total number of pixels, we multiply the width by the height. So 800 times 600 equals 480,000. This means the complete bitmap image contains 480,000 individual pixels. So remember the formula. Total pixels equals width times height. Question 5. Why does pixel position matter? Why is the position of each pixel important? The correct answer is B. Changing pixel positions can change the appearance of the image. Look at these two examples. Both images use the same black and white pixels, but those pixels are placed in different positions. In the first image, the black pixels create a diagonal pattern. In the second image, they create a horizontal line. So even when the colors are the same, changing their positions can create a completely different image. Remember, both pixel color and pixel position are important when reconstructing a bitmap image. Question 6. 1 bit per pixel. Why can 1 bit per pixel represent a 2-color image? The correct answer is C. 1 bit has 2 possible values, 0 and 1. We can calculate this using 2 to the power of 1 equals 2. So with 1 bit, there are exactly 2 possible binary values. For example, 0 can represent white, and 1 can represent black. These 2 values allow each pixel to choose between 2 different colors. So remember, 1 bit gives 2 possible values, and therefore can represent 2 colors. Question 7. Binary to pixels. Suppose our color convention is 0 equals white and 1 equals black. We are given the binary sequence 0, 1, 1, 0. What pixel pattern does this represent? The correct answer is B. White, black, black, white. We simply convert each binary value using the agreed color convention. The first 0 becomes a white pixel. The next 2 ones become black pixels. And the final 0 becomes a white pixel. So remember, 0 becomes white and 1 becomes black. Using the correct color convention allows us to convert binary data back into pixels. Question 8. Pixels to binary. Here, we use the color convention. 0 equals white and 1 equals black. We need to convert this row of pixels into binary. Let's read the pixels from left to right. The first pixel is black, so it becomes 1. The second pixel is white, so it becomes 0. The next 2 pixels are black, so they become 1, 1. And the final pixel is white, so it becomes 0. Putting these values together gives us 1, 0, 1, 1, 0. So the correct answer is B. 1, 0, 1, 1, 0. Remember, each pixel is converted into a binary value according to the agreed color convention. Question 9. Color convention. 2 computers receive exactly the same binary sequence, 0, 1, 1, 0. But the 2 computers use different color conventions. Computer A uses 0 equals white and 1 equals black. So it displays white, black, black, white. Computer B uses the opposite convention. 0 equals black and 1 equals white, so it displays black, white, white, black. The binary sequence has not changed, but the resulting pixel patterns are different. Therefore, the correct answer is C. The computers will produce opposite color patterns. So remember, binary values only have the intended meaning when we know the encoding convention used to interpret them. Question 10. Reading order. In our simple bitmap examples, how are pixels converted into a continuous binary sequence? The correct answer is C. Left to right, then top to bottom, row by row. We begin with a top row. We read each pixel from left to right. When we reach the end of that row, we move down to the next row. Again, we read from left to right. We continue this process until every row has been read. The binary values from all the rows can then be joined together to create one continuous binary sequence. So remember, read left to right, starting at the top, and move downward row by row. Question 11. Why does width matter? We are given the binary sequence 0, 1, 0, 1, 1, 1, 1, 0, 1, and we know that the image width is 3 pixels. So how should we divide the binary sequence? The correct answer is B. 0, 1, 0, 1, 1, 1, 1, 0, 1. Because the width is 3 pixels, each row must contain exactly 3 bits. So we divide the sequence into 3 groups. 010, 111, 101. These 3 rows give us a 3 by 3 pixel grid. This is why the width is important. It tells us where one row ends, and the next row begins. So remember, the image width helps us correctly reconstruct the pixel grid from the binary sequence. Question 12. Reconstructing an image. We are given a binary sequence, along with an image width of 4 pixels and a height of 5 pixels. We also know that 0 represents white, and 1 represents black. What should we do first to reconstruct the image? The correct answer is B. Split the binary sequence into rows of 4 bits. Why 4 bits? Because the image width is 4 pixels, so every row must contain exactly 4 pixel values. The sequence becomes 0, 1, 1, 0, 1, 0, 0, 1, 1, 1, 1, 1, 1, 1, 0, 0, 1, 1, 0, 0, 1. We can then convert each 0 into a white pixel, and each 1 into a black pixel. This reconstructs the original 4 by 5 pixel image. So remember, the image width tells us how many bits belong in each row.